Hey guys, I'm going to cover some of chapter 6 with you. I'm skipping some of the beginning parts. You guys can go over this on your own and some of the history behind the atom. I'm going to start here with the modern model and then go over electron configuration. And so go over the first part of the notes before you watch this. The modern model of the atom is the one that we still use today. And it's called the wave mechanical model, which replaces the Bohr model's orbits with what we call orbitals. So instead of circular energy levels from the Bohr atom, orbitals describe regions of electron probability. And so these are regions where electron probably is, but we're not quite sure. And so we have these regions where the darker, denser regions, that's probably where the electron is. It's less likely around here. It's very unlikely anything that doesn't have any of this density here. And so here for energy levels, like the Bohr atom, the modern model has energy levels. We call these principal energy levels. And we represent them by N equals 1, 2, 3, 4, and so on. So N is representing these different energy levels we have inside an atom. And then each energy level or principal energy level consists of sublevels called orbitals. These orbitals vary in shape and energy. And so they have these weird shapes. And that is representative of the type of energy they have. And each orbital can hold 2 electrons. So that's important. We have energy levels with orbitals. Each one can hold 2 electrons. So here are the types of energy levels. The S is the simplest. Every energy level has it, starting from 1, 2, 3, and so on. So there's 1 orbital per energy level. So we're going to go over this and then practice, and it makes more sense as you practice it, and then you will kind of understand where this is all coming from. But here's the 1s, here's the 2s, and here's the 3s. So you see it has these nodes here as you add an energy level. It's the simplest, and it's just a circle. And then you have the p orbital, which look like these dumbbells. It starts on energy level 2. So the first one does not have any p orbitals. And from then on, each energy level has one. And there's 3 orbitals per energy level. And remember that each orbital can hold 2 electrons. And so at each energy level, there's 2 electrons that can fit in each p, so a total of 6 electrons. The d orbital starts on energy level 3. So that means that 1 and 2 does not have one of a d orbital. And there are 5 per energy level. So there's 5 of them, and they can each hold 2 electrons. And then we have the F, which is more complex, 7 per energy level. It doesn't start until energy level 4, and each one can hold 2, and they're very odd looking structures there. Okay, so in these orbitals, each electron is spinning, like a top spins on its axis, and they're spinning in opposite directions. So if 2 electrons are occupying an energy level, we often represent an energy level or an orbital by a underline or a box like this, and we put the electrons in there as arrows. So we represent that they have different spins by having one arrow go up and one go down. So you can do half arrows or you can complete them like that. But these 2 electrons have to be spinning in opposite directions, and this is called the Pauli exclusion principle. And then the next rule is the off-ball principle, which means that the electrons are going to want to occupy the lowest energy level that can receive it. And so here is energy going up, and here are the orbitals in terms of their energy. And so instead of drawing the big fancy pictures, we just draw these orbitals in terms of boxes. We say what their N energy level is, and then what type of orbital it is. So there's a 1s, a 2s, a 2p, 3s, 3p, 4s, 3d, 4p. And in energy, it increases going up. So s orbitals are the lowest in energy. And then, so you're going to want to fill that first. And so then you go to the 2s, you fill that, 2p, fill that, 3s, 3p. Notice that s is so much lower in energy that the 4s is lower in energy than 3d. And so that would fill before the 3d. And so what we're trying to do is figure out when we have an element, where are those electrons? We're trying to figure out where are we going to put them. And when we put them in, we always start from lowest energy level and you fill until you get to the higher one. And when we're filling orbitals, as we're doing that, orbitals of equal energy are each occupied by one electron before any orbital is occupied by a second electron. And it has the same spin. So what that means is that if you have the 2p orbital, so say you've been filling it, you've put 2 electrons here, 2 electrons here. In the 2p, you have 2 electrons. Instead of putting them both in here, you're going to spread them out and have the same spin. And so if we were adding another electron here, so we put electron, if we put another electron in here, we'd first put it in that third one, and then we would start pairing. And then we could put one in there, and one in there, and one in there. And so this is talking about where the electrons go as we're filling them. And so what this gets us into is electron configuration. It's basically like an address for these electrons in the atoms. We want to know where they are, because when we know where the electrons are, then we can know how they're going to bond to other atoms. And so we're going to get a picture of what these electrons look like in the atoms. Instead of drawing the orbitals, though, we just draw boxes and we fill them based on their energies. So for example, hydrogen has 1 electron. And so that 1 electron, here is this energy diagram here, is going to go in the lowest energy orbital. So in there, and when we write out what's called the electron configuration, we'll say it's 1s1 because there's 1 electron in that first orbital. Helium has another electron, so then we're just going to put it, because this is still lowest energy, we're going to pair it with that one. If it was up here, we would want to fill all of these, but since 1s only has 1 orbital, we're just going to pair it there, and so we have 1s2. Lithium has 3 electrons. I'm getting this from the periodic table. We've got 1 electron, 2 for helium, 3 for lithium. And so that third electron goes in the next energy level. Beryllium comes along with 4. It's going to pair in this next one. Then boron comes along. It's got both of these filled. So we're going to start filling right there. So we filled these, and then we'd fill that. If you came along with the next one, carbon, you would fill that one because this is the same energy. It's on the same energy diagram, the same place of energy. And so you want to follow Hund's rule, put 1 in each one until you pair them. They want to be alone and they want to be spinning the same way. Then when you get to nitrogen, you'd add another one. And then you would get to oxygen, add another one. Fluorine, add another one. Neon, add another one, and so on. Here are more examples of how we did this, and this is basically what I just showed you of orbital notation, which is where you actually draw a line for those orbitals and fill them with electrons. An electron configuration where you're just writing how many are in each orbital. And so you're going to say 1s, 2s, and then how many electrons. If you add up all of these, you'll get the same number of electrons as are in the symbol, the element. So neon, if you look at neon, it has 10 electrons. Its electron configuration has 2, 4, 10 electrons. So a lot of this is just practice until you get the right, get the hang of it. And so here, an order of filling shows you the order that these are filled. And so we're going to start with sulfur. Sulfur has 16 electrons. So 16 electrons. So we're going to just start filling for electron configuration. We'll do 2 in the 1s, and then we'll put it in 2s, 2, and then we'll put 6 in 2p, 6, 8, 10, that gives us 10. And so then we'll fill the 3s, 2, and then the 3p is the last one. We've got 2, 4, 10, 12. We need 4 more electrons, and so we're going to put 4 in there like that. For orbital notation, we're going to just draw a line for the 1s, fill that, 2s, fill that, 2p, fill that, and then the 3s, and then the 3p is where we will fill with 4. So I put 3 and then I pair it. And so this is where we are obeying Hund's rule, where we're going to put 1 in each before we start pairing them. Okay, next I'm going to do the same thing with titanium. Titanium is right here. It's got 22 electrons. And so the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and so that gets me to 2, 4, 10, 12, 18, 20. And so this is where I'm going to stop with 2 electrons right there. Orbital notation, 1s, fill that, fill that. This is obviously much more tedious. 3s, 3p, fill that, 4s, and then 3d. 1, 2, 3, 4, 5. Like that. That's how I will put those 2 last electrons in there. So notice that this can get pretty tedious here. Noble gas notation is a way we simplify this. And so basically what we do is we look at the noble gas in the row directly above the elements. We enclose that in square brackets and then represent that as the electron configuration, and then just do everything after that. So for example, so here are the noble gases here in this column right here. And so if we were going to do titanium, you go up 1, down to its noble gas, and say it has everything argon has, and then it has, so that's 18 electrons, and then it has whatever's left over, which would be 4s2, 3d2. And so we're going to do some examples here. For rhodium, which is right here, number 45. So there's 45 electrons there. So electron configuration, starting from here, go up. We get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and that gets us 2, 4, 10, 12, 18, 20, 36, 38. And so we've got 7 left. 1, 2, 3, 4, 5, 6, 7. And so the next one after 5s is 4d. And so we do 4d7. What noble gas notation does is it says find rhodium, go up, down to its noble gas, so that's krypton. Put that in brackets and say it has everything krypton has, which is 36 electrons. The key here is that the noble gas always ends on a P6, so you go back to your last P6. that should add up to the 36 we need. 2, 4, 10, 12, 18, 20, 36. So everything krypton has, and then 5s2, 4d7, like that. Then when we do our orbital notation, say it has everything krypton has. So krypton goes all the way up to here, and then we only have to do that. So then it has 5s2, and then 4d. 4d, 1, 2, 3, 4, 5, 6, 7. So much easier. Again, noble gas notation for iodine would be, so iodine is all the way down here, so it's even longer. Electron configuration is long, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10. So that's 2, 4, 10, 12, 18, 20, 36, 38, 48, and iodine's 53. And so then in the 5p, I would have 5. Noble gas notation, we're going to go up 1 and over, so it's also krypton. And so krypton is 36, and you're going to go to your last full P6, which is right here. And that ends up being the 36. And so you say it has everything krypton has, and then it has 5s2, 4d10, 5p5. So then draw the orbital notation. Krypton, 5s, 4d is 1, 2, 3, 4, 5. It is completely full. 5p is 1, 2, 3, 4, 5. Like that. Okay, so here we're going to notice a trick. If you look at the electron configurations, as you go along the periodic table, let's notice a pattern here. So it's 1s1, 1s2, and then we've got 2s1, 2s2, 2p, 1, 2, 3, 4, 5, 6, 3s1, 3s2, 3p, 1, 2, 3, 4, 5, 6. Notice how the periodic table is broken up into blocks that are same as the orbitals. And so here you've got 2 spaces here. This is your S block. Here you have 6, 1, 2, 3, 4, 5, 6. This is your P block. Here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's your D block. Down here, these weird guys here have, don't count these because these are supposed to be up there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is your F block. So the easier way to do electron configuration is when you're given an element to use this pattern here. So for example, to do sulfur with this. So here is the pattern of how it is. Here is where sulfur is. And so the electron configuration then for sulfur would be 1s2, 2s2, 2p6, because it's filled, 3s2, and 3p, 1, 2, 3, 4, like that. Notice how everything here, the P's and the S's line up with the periods. The D's are always one behind, so 4s, it goes to 3d. And then the F's would end up being 2 behind. We're not going to do a lot of F orbitals. I'm going to stick with S, P, and D because the F's get weird. So gallium here, let's try that. We do 1s2, 2s2, fill that, 2p6, 3s2, 3p6, 4s2, fill that, 3d10, and then you've got 4p here, 4p1. It's also easier to do the noble gas configuration because here, if you wanted to do that for sulfur, you just cut it off there and just start from below. And so above sulfur is neon. And so it cuts off there. And that's why noble gases always end on P6, because they end at the end of that P block. And the same here for gallium. You'd cut it off there and then just do 4s2, 3d10, 4p1. Okay, so this can get a little tricky just to see all of this. And so I suggest that you kind of go over these, go over the practice problems. Basically what we did is started with using this energy diagram here, but then once you kind of get the hang of that, you can start to see how it fits on the periodic table. So look at this chart, and as you fill, this is going to tell you how to fill it. And so basically you're just going to find your element and then fill until you get to the end of that. Okay, the last thing is the periodic trends as you are going on the periodic table, how things are trending, what you can figure out about the elements. Atomic radius is basically the size of an element. The way it's defined, this is how they calculate it. They take two atoms together, they calculate in between the nuclei and divide it by 2 because that's the easiest way to get how big it is. But it's basically telling you the size. The trend is that it decreases across a period. As you go across, it decreases, the positive charge of the nucleus increases. And so as you go across, you'd think it would get bigger because you're adding electrons, but you're also adding protons in the nucleus. And so that means that it's pulling all the electrons in tighter. And so as you go across, the nucleus pulls it in tighter and the element actually gets smaller. So the number of protons increases, causing the size to decrease. So it decreases as you go across. And then it increases down a group. So as you go down a group, it increases because you're adding energy levels. So it increases down a group because you're adding principal energy levels, and so the element is getting bigger. The next is ionization energy, which is basically how much energy is required to steal an electron away from that element and make a positive ion. And so ionization energy, it makes sense that as you go across, it's going to get harder as the positive charge of the nucleus increases. It's more difficult to steal an electron as you're adding protons to the nucleus. So the protons increases across a period, making it more difficult to remove an electron. And as you go down a group, you add principal energy levels. That electron is further away from the nucleus. The nucleus doesn't care about it as much, and so you can take away easier as you add principal energy levels. And so it decreases down a group. That's the difficulty of taking away an electron. It gets easier as you go down. So the ionization energy decreases. So here are the trends for this. They're the opposite basically. Atomic radius increases as you go over here and down. Ionization energy increases up and over. And so as you move across a period, the number of protons increases, causing the positive charge of the nucleus to increase. And so atomic radius decreases, ionization energy increases. As you move down a group, the number of occupied principal energy levels increases. This causes the atomic radius to increase and the ionization energy to decrease. So if we were to compare sodium and cesium, Which is larger? Well, cesium's lower, has more principal energy levels. It would be lower. Which has the lower ionization energy? So which one is it easier to steal an electron from? Again, cesium's down here, the electron's further away from the nucleus, and so it would have the lower ionization energy. Fluorine and bromine. Which is larger? Again, bromine here, which has the higher ionization energy. And so ionization energy increases as you go up. So fluorine would have that because these electrons are closer to the nucleus, harder to steal away. Potassium and bromine, here we're comparing across a period. So which is smaller is the question. The smaller one is going to be bromine, right there, which has the lower ionization energy. So as you go across, it gets smaller, but it also gets harder to take away the electron because there's more protons. And so the lower ionization energy would be potassium here. Okay, so that is the end of this chapter. Again, go over your practice worksheets. Email me if you have any questions.